taken calculus before, you may think that the integral is the same thing as the antiderivative, but this is actually not true. The Heaviside step function, for example, is integrable, but it has no antiderivative because of this jump discontinuity at the origin. Another example is the derivative of Volterra's function. So this has an antiderivative, which is Volterra's function, but it's not Riemann integrable. So what conditions do we have to place on f such that we get the conclusions of the fundamental theorem of calculus, which essentially states that the integral and antiderivatives are the same thing? So if f is continuous on this closed interval, then we actually do have that the integral and antiderivative exists and are equal. But what if f isn't continuous? There are many circumstances in which f is not continuous, and we do get the conclusions of the fundamental theorem. For example, an example, something like this. So little f is equal to 2x sine 1 over x minus cosine 1 over x when x is not equal to 0, and 0 when x is equal to 0. So the graph of the function would look something like this. And so this is, f is not continuous clearly, but it does have an antiderivative, and it is integrable, and the integral is equal to the antiderivative. So what's going on here? Well, the fundamental theorem of calculus has conditions, right? The conditions are that f is integrable, so you can take Riemann or Lebesgue integrable, it doesn't matter, on this closed interval, and that f has an antiderivative big F. So in other words, there's a big F, a continuous function on the closed interval and differentiable on the open interval, such that the derivative of big F equals little f on the open interval. So under these conditions, we have the fundamental theorem of calculus's conclusion, which is this in blue here. Essentially, it states that the integral is equal to the antiderivative. So as a final remark, if you think the existence of an integral and the existence of an antiderivative seems like too much to ask, right? Seems like the hypotheses are too stringent on the fundamental theorem, remember that you can use the fundamental theorem of calculus piecewise or in conjunction with limit arguments. So for example, in that first example of the Heaviside step function where we couldn't apply the fundamental theorem of calculus because this function doesn't have an antiderivative on its whole domain, we can still apply the fundamental theorem on the left side of the domain and on the right side independently, and combine these two to find the integral over the whole domain.